Today we want to finish up section 1 by doing some calculations that are involving pH, and we're going to calculate the hydronium ion concentration from the pH. So here is sample problem D. It says determine the hydronium ion concentration of an aqueous solution that has a pH of 4.0. So we've been given that the pH is 4.0 and that we're supposed to calculate the hydronium ion concentration. So what is going to be our solution? Well, we know from the discussion of yesterday that the hydronium ion concentration is equal to 10 to the negative pH, or the antilog of the negative of the pH. So by putting in on our calculator 10 to the x, and in place of the x put in negative 4, and press enter, we find out that the hydronium ion concentration is 1 times 10 to the minus 4 molar. Sample problem E. The pH of a solution is measured and determined to be 7.52. So this is one of those pHs that's not a whole number, definitely needs to be done on a calculator. And they want us to figure out what is the hydronium ion concentration, and then what is the hydroxide ion concentration. And then at the very end, we're going to determine from those concentrations whether the solution is acidic or basic. So we've been given that the pH is 7.52. pH is 7.52, and we're first going to figure out the hydronium ion concentration, the hydroxide ion concentration, and then is it acidic or basic. So first of all, in our solution, we're going to use the similar problem or calculations like we did in the previous problem. The hydronium ion concentration is 10 to the negative 7.52. I'd again strongly encourage you to practice this on your calculator to make sure that you're getting the correct answer. And if you put that in there using the 10 to the x button, and in place of the x you're going to put in a negative 7.52, and we find out that the hydronium ion concentration is 3.0 times 10 to the negative 8th. Now that we know that the hydronium ion concentration, we can then calculate the hydroxide ion concentration, because the product of the hydronium ion concentration and the hydroxide ion concentration is 1.0 times 10 to the minus 14. That was a number I wanted you to memorize. And if we solve for the hydroxide ion concentration, we're going to take the 1.0 times 10 to the negative 14 and divide it by the hydronium ion concentration. So we'll have 1.0 times 10 to the negative 14th divided by 3.0 times 10 to the negative 8, and we find out that our hydroxide ion concentration is 3.3 times 10 to the negative 7th molar. So from the, and we have to determine if this was acidic or basic. If we look at the hydroxide ion concentration, it is a little bit greater than our hydronium ion concentration. So that means that it's going to be basic. Or another way of looking at it, our answer for the hydroxide ion is 3.3 times 10 to the negative 7. If it had been 1, it would have been neutral, but we're a little bit greater than that, so we're on the basic side of the pH scale. So in these relationships that we have between the hydronium ion concentration, the hydroxide ion concentration, and pH, we can look at some of these examples that we have here. Looking at the first one right here, we find out that the hydroxide ion concentration when it ionizes is going to be equal to the concentration of the whole formula unit, potassium hydroxide. And so that means that the hydroxide ion concentration over here will be the same as the concentration of the potassium hydroxide. So we know the OH. Then to calculate the hydronium ion concentration, we're going to take 1.0 times 10 to the minus 14 and divide it by this number right here. And that will give us 1.0 times 10 to the minus 12, 1.0 times 10 to the minus 12. And then if we take the negative of the log of the hydronium ion concentration, we find out that the pH is going to be 12. Okay, pH is going to be 12. Comes from this part right here. Now on this next one over here, we see that this is ammonia, and that's the concentration of ammonia. And the ammonia, when it reacts with water or is placed into water, gains a proton or a hydrogen ion from the water, making it NH4. If you remember that previous chapter, we did that. And that leaves us with a hydroxide ion concentration, and it should be all in a 1-to-1 ratio. So you would think that the hydroxide ion concentration would be equal to this, but you'll notice that it's less than this. And that's the reason why we have stated that this ammonia is actually not completely ionized. And since it's not completely ionized, this amount right here is going to be smaller than you'd expect. And you'd think it'd be a very strong base, but it's not all that. It's kind of a medium kind of base. And then when we look at the next one, we have pure water. Remember, when pure water, it's capable of self-ionization. We'll have some water molecules, or mostly water molecules in solution, but we'll have this type of concentration of the hydronium ion, and we'll have this concentration of the hydroxide ion. And using this and the negative of the log of the hydronium ion concentration gives us a neutral pH of 7.00. Okay. Next example is 1.0 times 10 to the minus 3 molar. And when this ionizes in water, we form one hydronium ion and one chloride ion. And they're all in a 1-to-1 ratio. So this is going to be the concentration of the hydrochloric acid. Why? And it wasn't up here, is because we know that hydrochloric acid completely ionizes. And so for every one of these, I get one of these. Now, if I take the negative of the log of the hydronium ion concentration, and I'm using this number up here at the top, the -3, will become my pH of 3. Now, if I want to calculate this, just remember that 1 times 10 to the minus 14 divided by this gives me this answer over here. And then on the last one, this is acetic acid. And we know that acetic acid is a weak acid. And when this ionizes, you would think that if it would completely ionize, that this would represent the concentration of this, but you'll notice that it is much smaller than that. So this, as well as ammonia, both of these are weak acid bases, and you have to measure them experimentally. So what you would do is you'd use like a pH meter, measure the pH, which comes out to a 2.87, and then put that into the formula of hydronium ion concentration is the 10 to the negative pH, and solve for the pH, and we'd find out, if we put in the pH and we solve for the hydronium ion concentration, we get this number right here, and then we can figure that one out. So two of these, you'd have to actually use a meter to figure out the pH, because we can't calculate these amounts directly because they do not ionize completely. They're weak. This top one here is a weak base. The bottom one was a weak acid. So just to summarize, the hydronium ion and the hydroxide ion can be calculated from these measured pHs. But if there's something that completely ionizes, we can actually calculate what the pH should be. So here are the kind of like a summary of what we did in this last one. This particular one right here and this one right here were not completely ionized, and so consequently the pH over here is not as expected. They would have to tell you the pH and measure it before you could actually calculate these values over here. Water, we know what it is. We learn these numbers right here, so we know that it has a pH of 7. But the others two given here, potassium hydroxide completely dissociates, so we can figure that one out. Hydrochloric acid completely ionizes, we can figure that one out. But some of these you have to just find out what the pH actually is. So the pH of some common materials are given here. You did a lab in which you try to figure out using cabbage juice as our indicator what pH something is. This tape dispenser that's up in the upper left-hand corner is a universal indicator tape, and it will change to all these different colors depending on what type of solution you're putting them in. And so battery acid would turn a bright red, stomach acid would be a yellow, apple juice would be a little lighter shade of yellow, coffee is about a pH of 5, water we know is being neutral at 7, and an acid like Tums would be about an 8, baking soda would be about a 9, hand soap is between a 9 and a 10, household ammonia cleaner is between 11 and 12, and if you have Drano, it's pretty potent stuff, is a 14. So that kind of gives you an idea of where these pHs are for common household substances.